Hey, good afternoon, everyone. This is Dan Jenkins. I'm with the Steel Camel. I'm down here in Tampa, Florida today. It's middle October and it's hot and humid. And today we're going to talk about how to control this humidity in enclosed spaces. Primarily about electrical junction box, motors, electrical panels, printed circuit boards, printed wire boards, that type of stuff. We want to preserve your parts and so they're not damaged. So that's what we're going to talk about. Okay, and to begin, we have to know that water is everywhere. We are made of water. Our food has water. Our air has water. Guess what? Our parts have water in it too. So there's some really good parts about water. They make the world go around, but there's some really bad parts about water, and we're going to explore those today. A little bit about me. I was involved in accident prevention and accident investigation for Shell Oil, and I primarily focused on heavy equipment and why things break and why things snap and why things fall apart and why people hurt themselves or unfortunately get killed. And during that time, I got to work with some reliability engineers who were focused on making sure these things didn't happen and how to make their operation work more smoothly. So I do have a little experience in that, and I'm going to try and relay that to you today, particularly about moisture in electronic parts. Okay. And as we talk about moisture on electronic parts, these things, again, cause accidents, cause part failure, cause disruption in your productivity. And one of the things I'd like to show you real quick is microbial influence corrosion, which is a kind of gaining steam in the industry as we have more alternative products, if you will. For example, ethanol and gasoline, corn packaging, popcorn, all kinds of organics out there that are more susceptible to micro influence corrosion. If anybody knows what kind of part that is, please put it in the comments section. Okay, so to set the stage, we're going to talk a little bit about the similarities between cranes and circuit boards and electrical parts. On the left is a big crane, on the right is a very small circuit board. But what makes them so similar? First, they are put together. They are assembled. A crane is put together, and so is a board. So we're assembling hardware. Secondly, they both transfer loads. So a board transfers current, but a crane transports parts or mass. Okay, very similar. They both use fasteners. A lot of fasteners used on a crane. A lot of fasteners used on printed circuit boards. And by the way, I ran into a guy who sells torque wrenches for cranes and torque wrenches for printed circuit boards. Same wrench, just scaled a lot farther down. So there's a lot of similarities on how they're attached and assembled. Also, they're both exposed to harsh environments. I'm in Florida. I'm on a saltwater. Across the bay from us is a power plant, coal-fired plant, and there's actually a gypsum board plant that gives off harsh environments. Cranes, as you know, have a lot of steel and they're welded. Two metal parts are welded together. In the circuit board industry, they just call it soldering. Very similar, just a much smaller in scale. What else? Cranes are subject to vibration. A lot of excavators and bulldozers and aerial lifts are all subject to vibration. Well, so is the motors in your plants. So is the server in your plant. The computer boards, they vibrate. They overload. They definitely are both susceptible to heat damage. So if you have heat in your server, because it's getting a lot of current, well, guess what? A crane gets hot if it's being worked a lot. The parts expand and contract, particularly if they're used all day and then cool down. If they're used very heavily and cool down, they contract. And of course, as we talked about, they're both subject to corrosion, and unfortunately, both can fail. Let's take a deeper look. Okay, let's talk about overload for a second. That was a picture from my company at a Navy base, by the way. And cranes get overloaded quite often. People don't read the directions, don't read the load chart, and they're susceptible to overloading, falling over, breaking. Okay. Printed circuit boards get overloaded. Too much current, too much energy is running through them. Next, cranes. You might have the best crane in the world, but if the load is rigged improperly, it could cause the crane to fail and the part to fail. Same with electronic boards and electrical junction boxes. These electricians could assemble them wrong, rig them wrong, and attach wires in the wrong place, and it's now not assembled correctly, and it can fail. Cranes have weak spots. They get fatigued if they get used over and over in the same spot. I happen to not only be on the crane prevention side, later in my career, I was on the crane repair side, and I worked for a company that repaired crane booms just like that. And they usually had a weak spot from fatigue or stressed out, and they failed. Same with a board. Electronic parts get weak, particularly if there's corrosion involved, and they can be stressed, and they can crack and fail. So keep an eye on for metal parts that get used over and over in the same routine, and guess what? They'll get fatigue and weak spots. Of course, there's corrosion. Corrosion on electrical panel. Look at the product on the left, top left. That is an electrical panel. Guess what? Water, moisture droplets were living in there, starting the electrical corrosion process. Bad, very bad, particularly if you're operating a crane. Okay, so it's also bad if you're in your plant. You could be operating the building or operating machinery or operating conveyor belts with electrical panels. We need to open them up and look in there and see if moisture has caused corrosion. Also, for those of you going out and inspecting your plants or your factories or your computer assembly places, you gotta look at the fasteners. You gotta look at the fasteners. They are susceptible to corrosion and fail, and they fail quite often. Okay, why? Because they get corrosion on them, they get moisture, they expand and contract, and once that oxidation process starts, it makes the fasteners very difficult to get out, and your part might not be working as it's supposed to. So look for those types of things. Also, cranes, unfortunately, and aerial lifts, unfortunately, are subject to sparking, particularly when they hit wires or they hit metal buildings. Okay, they cause a fire. Well, same for your parts on your electrical parts. They're susceptible to spark or fire. So you have to look inside and see if there's any moisture, any corrosion, anything that's getting hot, too hot that could spark a fire or cause a short. So moisture causes some of those problems. Okay, let's talk a little bit about harsh environments. And if anybody has in the chat room wants to talk about harsh environments, please chime in. But I started in the offshore oil rig business, perhaps one of the most aggressive corrosion situations known to man. I think the gas station business is actually surpassing it, but they're very harsh environments. Why? We have humidity, we have salt air, we got lots of machinery that gets hot and cold, and guess what? We have corrosion. So look for harsh environments: tire plants, phosphate plants, pulp and paper mills, fertilizer plants, orange juice factories. Anybody guys are doing perfume or vitamins, right? You're giving off acid. That acid mixes with the moisture, lands on your part, causes corrosion. So look for the elements that you're working in. Alrighty. So let's talk about moisture. What is it and why is it so destructive? Okay. Well, the moisture, again, it's everywhere. It's in our atmosphere. It's in our shower. It's in our iced tea. It's in our stomach. It's in our food. So moisture is everywhere. But when it mixes with a little acid, it begins to destroy and eat surfaces. When that happens, we get little pits and holes. We can get a leak. We get weakness. Okay. And if you have your parts expanding and contracting when it's hot and cold, guess what? Further accelerates the corrosion, further accelerates the weakness of the metal parts. Also, moisture is part of microbial corrosion, which we talked about earlier. we got corns, we got starches, we got proteins. We have all these things in the air which are organic. They mix with the moisture, and it creates what we call acidification. And that is particularly bad when you have acidification and lots of changes in temperature. A lot of people think they should park their planes in Phoenix because it's dry. Great. Unfortunately, you got bigger temperature changes in Phoenix. So they still have humidity and they still have corrosion problems. Okay, let's also talk about this picture right here and why this plane on the left is such a humidity magnet, in particular in the cockpit. This is taken in the Persian Gulf, Desert Storm, and the tarmac is 100 degrees, okay? The plane is 110, sun beating down on it all day. The guy fires up the engine, now the plane is even hotter, okay? Now the pilot gets in, super hot, turns on the air conditioner and pulls on the canopy at the exact same time. What happens when you have hot temperatures up against a cold temperature? In the case of this, you get humidity, and it is actually a humidity magnet. It is humidity central. Okay, if you want humidity, have hot surfaces and cold air inside. And as a matter of fact, the humidity was so strong and so much in this picture, there are actually little water droplets, little drops of water beating up on the canopy, and when they would release, they'd actually fall on the electronics and cause damage, and big damage. So this is kind of how we got our start, Steel Camel did. We're very familiar with enclosed spaces where it's hot and cold, you got temperature changes, and now you have humidity. And what do you do to stop it? What do you do to mitigate it? All right, let's talk a little bit about things being destroyed and things being eaten, okay? So we got to look again for these humidity magnets, which are enclosed spaces, or places on a crane or a piece of heavy equipment or electrical box where moisture develops and it sits on the metal for quite some time, and the process starts. So keep an eye out for where water sits. Let's basically review some principles. So metal's negative, moisture's positive. They're looking for each other. They're constantly looking for each other. And when they start to release some of their properties, we get some oxides and we get some rust. And most people, if you go into your garage, you'll see some rusty tools there. So that's the basic principles of what's happening. So what do people do to stop corrosion? Well, for almost thousands of years since the Iron Age, people have tried to put a barrier in the middle. So most people are familiar with paint is a common one, or grease. And we try and keep the water or the moisture away from the metal. So that's the most common way, is people put up a barrier. So let's take a little deeper look. Historically, in the Iron Age, in the Middle Ages, we first had armor for soldiers, so swords and shields and helmets. How did they protect them from rusting? Well, early on, they used whale blubber, and they used olive oil, and they used animal fat, and they did all kinds of things to create a barrier to keep that moisture away. And they still use that today. In many cases, it's very effective. There you go. There's a little history. So we've had these armor, and people from all over the world have tried different things to protect it from rusting. Okay, let's move on a little bit. What are some other things that people have done to protect metal? Some people use waxes. Some people use oil. Some people use grease. Some people use lanolin. So lanolin is very popular, and waxes are very popular. Let me turn that off. Okay, waxes are very popular. And so there are some good things that are very successful to protect electronics. Here's some more modern ones. Conformal coatings. It's kind of like a latex glove. It's basically a flexible latex that's skinny, and it can keep moisture off. Okay, I happen to work in the films, which are very, very, very thin oils. They even have what's called ultra thin now for aircraft parts. And some of you guys may be familiar with potting, which is like a very thick resin. And we try and smother the electronics and prevent anything from getting in. So that's called potting. If you drive by a gas station today and you look at the sign that's blinking and has a big Sunoco or a Shell sign, that thing probably has a potted printed circuit board and a potted electrical panel, and they just try and smother it with resin. And again, there's many successes of it. Okay, but there's also some other types of barriers. One is called a satisfier. Some of you guys know of anodes that are put on boat motors or outboard motors to try and distract the energy transferring or try and divert the energy. Those are called satisfiers. That's the kind of the technology we represent, that the metal is looking for something positive and it finds something else that satisfies its need. So those are called satisfiers. There's some other words for it, but that's the term we use today. All right. So I'd like to talk to you today about problems with barriers and what inspectors should look for. So as your reliability engineer, whether you get out yourself or you have inspectors around the plant, you need to be looking for telltale signs of what can go wrong. Okay, so what should you be looking for as an early warning sign? So one thing you want to look for is the paint peeling, or is the oil coming off? Whatever you decide to protect, is the barrier adhering? Yes or no? And why isn't it adhering? A lot of times it's surface prep. Nobody in the world likes to do surface prep, and so there's a lot of poor surface prep in the world, and it leads to paint peeling. So that's one thing to look for. Other things to look for is trapping moisture, where you have a change in temperature, you have condensation building up on your parts, and then you put the coating over it. If you look at the bottom right picture, that is a common problem in the auto painting industry. They do all this prep work to get your car ready for paint, yet there's moisture in the air lines, okay? And now they're painting your car with moisture in the airline itself and microscopic moisture on the car surface, and guess what? The paint won't adhere. So that's a problem. Big problem is moisture trapping. So look for any bubbles like that. Another thing you want to look for is a swelling or cracking. Is anything being deformed? Okay, again, I was in the crane accident prevention business, and we went around all day long looking for things that were cracking or swelling or expanding. So keep an eye on that. So those are some things you and your team should be looking for, early warning signs. What else should they be looking for? What else? So let's start over here on the left. On the boards, on the electric boards, look for any pitting or popcorning, kind of like a zit, if you will. It's just an expansion of metal really fast, and it pops, and it creates a little pit or a little hole or a little bubble or a little zit. And that's a problem when you have moisture landing on your parts. Another thing to look for as an inspector, is there anything that's disconfigured? You start off with a beautiful part, and now it's changed its shape. Well, why did it change its shape? So those are things to look for. Next, let's talk about bending and flexing. As we talked about earlier, the cranes and the boards both bend and flex. That's a good thing. However, it could lead to bad things if it's excessive. So look for cracks in coating, particularly you guys using any waxes, any resins, any conformal coatings. Look for cracks, because if you have a crack, the moisture is microscopic. It gets underneath that crack or through the crack, and then it sits on the metal, and now you have a coating covering moisture, and the inspector can't see it. And that's a major problem, major. Of course, look for cracks in metals, okay, particularly in your electrical panels, right, where there's surges or there's guys working on it, and something happens where there's a crack or there's a crease. Then finally, if you're a reliability engineer and you get a report that something is delaminating, something's not sticking, okay, or something is not fusing together and it's coming apart, that's a telltale sign that you got a problem and you got to nip it in the bud. So look for anything, any resin that's not sticking or not adhering or coming apart. So those are some things you should look for. Okay, let's talk now about, well, how do you control moisture? What are some things you can do? Okay, today we're going to talk a little bit about desiccants. And most people are familiar with them. They're little dried pieces of sand or dried pieces of earth that you would get in your beef jerky or you'd get into your pill bottle. And they're used today, still used today, heavily by the military and the computer industry. And basically it adsorbs a little moisture. Okay, but it was used by the military in the 40s. And when they came back from the war, in World War II, they noticed that a lot of things had corrosion on them. Okay, so in 1966, they enacted the first specification on trying to dry military parts or keep military parts dry on moisture-sensitive devices, and it's called Mil-Spec 3464. If anybody needs a copy of it, happy to send it to you. It's still in use today. It was actually written on a typewriter. Okay, and then that device, those beads, if you will, some people call them beads, okay? Silica beads is a common name. That technology was adopted by the computer industry in the 90s. So the Joint Electric Device Engineering Council and the Institute of Printed Circuits. Those are the two major computer board or printed wire board industry associations. And they advocate those today, primarily for shipping and just getting it to the next destination. And today, I'm proud to say, that the United States military, JDEC and IPC is actually looking at new technology and new ways to keep boards and electrical panels dry. So that's a good thing. Okay, let's talk about what does a desiccant bag do and how do they work? Okay, so the first one is silica, which again is dried sand. Silica sand is a dried piece of glass. They heat it up very, very hot, okay? And it's very rigid, and the moisture in the confined space actually adheres to it and coats the surface. So that's how silica works. Works on a little vapor pressure differential and a little bit about equilibrium, trying to make the container equilibrium. So that's how silica works. Basically, the moisture coats the surface. That's how that works. But there's also another one called polymetric. Most people are familiar with baby diapers. Baby diapers is a fascinating, unbelievably great invention. And that works by water being absorbed into the bag, and it gains weight. The problem with baby diapers, they do not pull moisture out of the air. So the baby diaper only works when water hits it. So it wouldn't be effective for you in a enclosed environment with just air. So that's basically how it works. The two principles, there's adsorb, coats the surface, absorb, becomes part of the bag. Okay. So again, we have a couple different kinds. We have a silica, which I mentioned is basically dried sand. We have some other ones that people use, which are clay or diatomaceous earth or fossils. Okay, so it's dried dirt, it's dried clay, it's dried earth. Okay, but again, the moisture just kind of sticks to it. And then again, there's polymetric. Okay, so if you're a reliability engineer and you start sticking these things in your electrical boxes or near your motors or near your computers or near your servers, and you want to keep that moisture down, how do you know when to change it? What is a telltale sign? So with the silicon clay, they often add a cobalt solution and it changes colors from pink to blue or red to orange, something like that. But it's kind of difficult if the bag is opaque. So that's a challenge. And the polymetric side, the inspector would look to see if it swelled, got hard, changed shape. And so those are some ways for your inspector to tell, hey, it's time to change the bag. Fred, do we have any questions out there? Any comments? Anybody like to quick comments or questions while we're going?
No questions in the questions tab, and a reminder for folks that do have a question or a comment to go ahead and type it in there.
Yeah.
Nothing at the moment. There's these different technologies. When you say the moisture gets trapped in the bag, is it chemically bound to
Yes,
the
chemically bound.
polymetric material? Is that what you
Yes,
mean? It
it's
gets
chemically bound.
trapped,
It
basically.
gets trapped and it
So
becomes part of it, and just like a baby diaper. Oops. So it's like a baby
can't wring
diaper.
them out, in other words.
So it expands.
Wouldn't want to in some cases. Yeah.
Yeah.
All
And the
right.
other thing.
Yeah, I'm not seeing any questions, so go ahead and drive on.
Okay, cool. So a lot of plants, particularly the computer chip manufacturers, electronic manufacturers, they have been buying the sand or the clay, and again, they want to regenerate it. And because it's an organic product, again, it's basically a piece of silica. It's unlimited. It's not going anywhere. So you could recharge the thing to your heart's content. I mean, 50 years, it's not going anywhere. It's never changing shape. It's never changing matter. Okay, so that's one of the benefits of silicon clay. You could recharge the thing over and over and over. With the polymetric, it's very limited because it's got some polymers in there and they get destroyed over time. Okay, let's talk about regeneration again. So if you use a lot of Deskin bags, what do? How do you regenerate them? Well, the two that are approved by the military, one is called a Clariant, right here on the left. That's the most common bag out there. You could actually recharge it, but you have to put it in the oven for 16 hours at 245 F to get your full use out of it. And it's like baking a turkey overnight, by the way. So that's the pros and cons of those bags. Yes, it can be recharged. You can use it indefinitely, but you got to put it in your oven for 16 hours. That creates issues as well. The polymetric, we go about 140 degrees in a few hours, but ours is limited in use. Okay, so let's talk a little bit about what actually happens to humidity in enclosed spaces with and without Deskins. So most of you took a shower today, you turn on that hot water, you get condensation on your mirror. Okay, so what happens in an electrical box or a computer storage box, you have this humidity that develops, and as it heats up, the top part of the humidity will turn into a gas, and it starts rising up due to pressure, and it will escape. So you leave the door open, the gases will go out the door. But when you put the lid on, it will trap it and it will fall back down and will puddle back up. And that's how you build up humidity in your enclosed spaces, because you have a lid on there and it's falling back down. So with deskins, what happens? What actually physically happens inside the box or inside the jar? So with the silica, it's called naturally occurring. The gases will rise and they will adhere to the surface. So as you can see on the left, they will adhere to the surface of the silica bead. On the right, which is synthetic, it will do so as well, but a little slower as the magnet starts to pull the moisture towards it. So on the surface, at the beginning, they both start to work. Then, as we go develop more heat and more pressure, the silica bead continues to absorb moisture and coats the surface. And so the beads will actually be coated and they'll adhere, the water will adhere. It's doing its job. Same with the polymetric, except on the polymetric, the moisture is now inside the bag. Big difference. And it holds it. As we get more moisture and we keep going on, as your product sits in your warehouse or in this hot machine, the silica actually reaches a saturation point and the moisture will fall back off and fall back into the atmosphere. That's when it's time to change. With the polymetric, it will actually hold and the moisture is not allowed to go back into the atmosphere, and so it will dry it for longer periods of time. So those are some of the differences. For those of you who have to follow industry standards, you're in the computer chip, you're supplying the military, I'd like to review a couple specs with you. First, if you're a military contractor, there's a spec called Mil-Spec 3464, which I explained earlier, which uses the adsorbent, which is the silica, still into effect this day. You go on the internet, there's 20 or 30 people that say they meet this spec. There's really only 2 companies that actually meet this spec, but there's a lot that say they meet this spec. So if you're doing military work, there's Mil-Spec 3464. If you're shipping computer parts and computer boards and making computer boards or shipping computer boards, there's 2 big standards out there. One's called JDEC, one's called IPC. And lo and behold, they both adapt the Mil-Spec 3464, which forces you to use silica. How about that? So that's kind of the specs out there. There's some specs for pharmaceutical, but I don't know much about those. And if you look to the right, on the right, there's a little thing called a humidity indicator card. That tells the operator, hey, you've got too much humidity in there. You need to change it. And then it says, hey, you really got too much humidity on your beads. Now you need to bake them, okay? So there is some other indicators out there, which is called a humidity card. And primarily it's used in the computer chip industry and the military, not too many other industries. Does anybody out there use humidity indicator cards? If you wouldn't mind, can you post a question there? Any questions on change indicators? Anybody have a question? Or anybody use humidity cards out there?
While they're finding their keyboards, is, one of the things is that there's a lot of variables, right? Where you are in Florida with way more humidity than where I am in California. I mean, I could probably work with the silica bag for quite a while before it changes the indicator at all, just because we typically run at 25 to 30 RH. It's not that humid, where I think your humidity is a bit higher than that most of the time.
Correct.
So I mean, it's really the amount of moisture you're trying to deal with. And do these standards deal with the well, how much silica do you need to put into a space, or is it
yes.
these
So
applications vary?
So JDEC and IPC have they call them units, by the way. So there's 2 unit, 4 unit, 6 unit, 8 unit, and the military lays that out in their specification. Okay, so it depends on how much you're shipping, how much you're storing. For example, there's a big electronic component manufacturer, shall rename nameless, but they have warehouses all over the world that supply the military, and depending on the volume of air or the volume of the box, they will use different units specified in the specifications. So they'll put bigger bags and more of them based on the volume of the package.
Okay, but the silica itself, I mean, there's probably some refinement as to how much more moisture it could have adsorbed to it, but there's a limit, right? There's surface area.
Definitely a limit. Now, some will claim that they have tiny microscopic holes in the beads of glass, but I have not seen any data on it from a third-party independent source. So leave it at that.
Right. Okay, well, I'm not seeing any questions. I think you're covering the material pretty well, so
okay, thank you.
That's a good sign.
So feel free to fire away any questions. So let's talk about this Mil-Spec. This is the dominant one. Again, this has been adopted. I have a copy if anybody needs it. It was written on a typewriter in 1966. And just so you know, to validate your deskant beads today, you can't do it because the equipment used in 1966 is no longer available, and you have to create it yourself. So it's quite complicated. So you have to go through the Department of Defense, which is very time consuming. So most people don't do that. So they just adopt what they got today. Okay, this comes to an important part for the reliability engineers who have moisture problems in their plant or in their facility, whether it's an electrical board, a data center, computers, light bulbs, whatever. How do reliability engineers do their own testing? Because you want to validate it yourself. Because right now we're waiting on the big defense contractors and the military to to upgrade the specifications and the testing. So how does one do it yourself? So the easiest way is to find some parts that you have, find the deskins here you have, and compare them in a humidity chamber. You can make your own, or you could do your own, or send it out to a lab. And you want to measure how much weight does the desiccant gain, and how long does it keep adding weight. So that's a good indication of how you conduct a performance test to determine which bag is the best for your facility. So one way is with the humidity chamber, very common. The second way, a lot of defense contractors do, who are concerned about humidity and storing electrical parts, before they get to that test in the humidity chamber, they take 2 mason jars, 16 ounce, 32 ounce, and they take 2 different humidity deskant bags, and they drop them in there with a piece of string. And then they put half a teaspoon of water in the jars, and then they put a heat lamp on it. And they see which bag holds the moisture and reduces the condensation in the jar. That's very common. So people do that with a heat lamp. Another way people test in deskant bags is they actually put it in the windowsill for a week, and they want a windowsill that faces the sun, where it gets hot during the day and cold at night. Hot in the day, cold at night, just like your warehouse. So a lot of people conduct their own performance tests before they roll out a rule at their plant. They conduct their own test, again, heat lamp or jar. Pretty simple to do. Finally, a lot of the big sophisticated companies that have operations all over the world, they're very concerned about the parts, like the ones I'm showing you in the middle. They do not want that humidity card to go off and turn colors before it gets to their destination, because then the customer can reject the entire pallet, or reject the entire truckload, or the entire train load if they have humidity. I just saw something this morning on cargo ships for marine, where the humidity is building up in these people shipping electric parts. So how can you conduct the test? Guess what? You take your package, you take your part, you wrap them up. I prefer to have a lot more air in it than these vacuum packs, and you put it out in your warehouse. You ship it around the world. You subject it to vibration. You subject it to hot and cold, and you try and develop real world experience and measure for yourself which one protects your parts the best, most economically. So that's another way to conduct a performance test. All right, let's move on. If anybody has questions, fire away. So what should you be looking for? You're a reliability engineer. You got these electronics, you got these parts, you got these motors, you got these servers, and you got to keep them up and running. So what are you looking for? How long does each deskant last, right? The United States military spends a fortune changing out deskant bags and heating deskant bags. That's very, very important to them, is the length of time that it lasts. That's very, very important to the military. Secondly, how much volume of air can be desiccated? So do you really want to shrink wrap all your parts? Do you really want to vacuum seal all your parts? I'm not so sure about that. So you want to test things and create a bigger bag or a bigger box and test it out. So you could have less packaging, which is a buzzword on sustainability, is less packaging, less waste. So the bag suppliers are going to be unhappy, and the box suppliers are going to be unhappy, but you're going to be able to desiccate a much greater volume of air. So that's something you can test for, because right now there is no official industry testing out there. Another thing you want to know is how well does each desiccant retain moisture? Because the last thing you want to do is put a desiccant bag in a critical part or a moisture sensitive device, and you dry it, and then all of a sudden you got it all dry, and now that moisture releases back into the atmosphere and right on your part. So you really want to talk and look at Can I retain the moisture? And then finally, for your inspectors who are checking on these critical devices, moisture sensitive parts, how easy it is it the inspector operator to determine when to change? That's very important. Again, some have the color, some people like it. Other people have the change in shape. Some people like that too. And so those are just some things for reliability engineers to look at so they can make sure nothing goes bad in their plant. Here's some of the big, if you do such a test, there's people that are interested in what your findings are. Okay. And finally, I'll wrap this up and then we'll open up to questions. I just want to share with you, as someone who's been in the business a while, that water's everywhere, moisture's everywhere. It's in our paint, it's in our cars, it's in our house, it's in our plant, it's in our electrical boxes, it's everywhere. And corrosion isn't too far behind. So with that, for a reliability engineer, pay attention to the water, pay attention to the moisture. And I think if you do that, you'll make your plants much more reliable. Thank you very much, and I'll stick around and see if anybody has any questions.
Right. One of the things, Dan, that struck me when you're talking about the differences in, holding moisture is earlier you talked about the silica, and I believe the clay also, the adhering, the absorbing, is they come to an equilibrium, right? And so if you're at 50 RH or higher, eventually, even with the desiccant bag, the interior will come to the ambient outside eventually. And it's just the desiccant bags in those cases just delay that process from occurring locally. Is that right?
That's correct. So, but you just got to be careful if you're sticking moisture to the surface. You don't want it to drop off and fall back onto your part. Okay. So
right. So it has to be sized to continue to adhere enough
yes,
moisture, and that's why there's the indicators to change it, right?
That's correct.
At some point it's at the point where it's getting close to saturation, so you got to change it out.
That's correct. And if you have like a big company and you have 500,000 parts and they're all boxed up and they're all critical parts, your labor gets pretty high if you have to change them out all the time. So
right.
that's an important
and
factor.
So part of it is sizing them, and all kinds of those things is part of it, but then they have it's not shelf life's not the right word, but they have a useful life before they come to equilibrium. And that'll depend on how much humidity it's dealing with and where
and what type of packaging is and what type of bag it's put in. So all these are factors. That's why there's no specs on it today other than this one that was written in 1967. So I'm grateful that the military and the computer industry is looking into it, because the more we change our boards, the more exotic metals that we get on there, the more susceptible they are to moisture.
Yeah, and I looked up that microbial stuff is, it's basically there's microbes that like to eat the films of, the kind of a thin moisture film that has a variety of different sulfides and ions and everything in it. And then a byproduct of those microbes is like sulfuric acid, which then is a key component in corrosion in a lot of metals. So I got a question for you from Randy. How do you recommend that electronics be tested against corrosion?
Not my deal.
You're in the business of just interrupting the moisture from being there. So Randy, it really depends on what kind of corrosion you're dealing with. The most common one that I know of is, there's two of them. One is just the temperature and humidity. The most amazing one I saw was, we had a young engineer want to put bare silver on a board. They needed to solve some circuit problem, so they put some silver down, but it was not pure silver, but it was closer to pure silver. It wasn't an alloy that captured the silver ions, the silver metal itself. And silver is called the mobile metal. So any electrical potential around it would create these beautiful tree structures of growth of this metal migrating across your board following the potential fields. And there wasn't moisture. I mean, moisture was involved in that, is that it got that process started. And so you could interrupt the moisture, but the silver, you just got to bind it chemically in the metals itself. You got to create a process that. So temperature and humidity, we typically would run 85, 85 for 7 days. If that corrosion due to those conditions, if corrosion enhanced by temperature and moisture, if that was going to occur, um, would usually occur within like 2, 3 days. It occurred in power the boards, and it would occur pretty darn quickly. The hard part is that sometimes corrosion on boards is caused by somebody putting their thumb on it, right? They put a little thumbprint on it, and your thumb is full of ions, essentially chlorine and sulfides, sulfur ions, essentially, or air pollution that contaminates the boards. And then you add a little moisture to the mix and electrical field to it, and now you got corrosion that your testing couldn't find. Another way to do it, in Dan, you talked about harsh environments, is one of the tests for some boards that are going into those environments is called a mixed flowing gases. And it's a cocktail of all kinds of things that are known to spark corrosion. And there's a variety of standards out there for doing that. So the be testing against corrosion is tricky because you have to have all the elements available for the particular kind of corrosion that you're interested in protecting from. And the hard one is when you have post-contamination to get that right. All right, got a couple other questions. Evan, I think Evan and Randy, I recognize your names as and a couple others, Ru and Long Chun, are common visitors to the webinar series, so welcome back. Evan talks about, can you go a little more detail about microbial corrosion? How prevalent and what is the mechanism by
Yes,
which
I can.
corrosion
I'm
takes
going to get
place?
to my favorite slide, if you don't mind. Okay.
Yeah,
All right.
your corrosion slide. There you go.
So microbes are microbial. You can't see them, but wait a minute. You can't see them there, but they're actually a living organism with a mouth and a pooper. Okay, and they excrement. I'm trying to use some of the best words I know. They take a poop, okay, and they release a slime, okay, and that's how they live. So they have water, they have protein, okay, they drink and they poop. And when they excrete a type of acid. There's many types of acids that'll make your head spin off on how many types of acids. So in order for them to live, they again create this slime, and they look for fuel, or they look for pollution, or they look for anything that they could hang on to, so they could build their own little kind of cocoon, if you will, and that's how they survive. They survive in diesel fuel. They just survive in your stomach, right? They survive in food, and so if you're and when they excrete that acid is when that acid attacks the metal. So there's some corns and there's some starches out there that are out in the atmosphere, and voila, that is from a gas station. And that is the nastiest corrosion known to mankind right there. And so microbial influence corrosion creeps into plants because, as Fred said, people put their human footprints, and they cough, and they have microbes, and they land on your parts. Does that help?
Yeah, so they're everywhere, and it's getting the right set of conditions for them to go. And the byproduct that creates the corrosion is their acidic environment that then attacks the metals or sealants or whatever. Yeah, it's something to be aware of. And that's why we paint things a lot of times. And so I've even seen paints in that say they're antimicrobial.
Correct. And another word you can look for, we're getting into chemistry here, pH adjustment. Okay. So if you're having these type of corrosion issues, okay, you may have to adjust the pH of your container. For example, the pH of this acid is about a 4.5, maybe a 5. It's nasty, and it bombards, okay, and it causes fuel to stop flowing. It stops pipes to leak. So some of the biggest oil spills in the world have been related to microbial influence corrosion. Pipelines cracking, pipelines breaking, pipelines getting holes in them, okay? So you may have to adjust your pH of your atmosphere to something that's safe. So you may have to add some kind of sodium or some kind of baking soda or something to lightly adjust the pH up a little bit.
So another question from Alan is, are there any design guides on when a board is subjected to steam environment? Well, one, I would say don't do that if you can.
I
But
could say
I mean,
this.
that's a lot of moisture.
Yeah, I could say this. The largest electrical connector company, I think, in the world, they are required to store these parts all over the world in boxes in warehouses, and they subject all their parts to steam aging testing. And that's about it. So I know that people do steam aging testing to see how they're gonna hold up over time, bombarded by temperature change.
I don't know of any guidelines out there. I think there are probably papers about protecting metals and polymers and adhesives from very high, from steam or from very high humidity and temperatures. But it gets down into the coatings and chemical composition of your boards as to how well it'll survive those things. You start getting into exotic materials you see under the hood of a car and down the hole of a oil exploration, rather than the common electronics. But yeah, they start to get pretty exotic, and I don't know of any design guidelines, so we'll go with that. Let's see, Evan, let's see, thanks, that answered it. So we'll go back to his question. Good, that's a good thing. Rue, can someone design a perfectly sealed enclosure and be done without desiccant or coatings? I have an answer for that, but
Yes.
Go ahead, Dan.
There's some things out there called hermetically sealed and nitrogen blankets. You're talking big bucks though, so that's my 2 cents on hermetically sealed but if you don't do it right, the microbe is still in there, so you could trap the microbe in there. So there are some people doing hermetically sealed and nitrogen blankets, but it's pretty not cost effective.
It depends on the application. I mean, there are calls for that. One of the things that I learned way back in Hewlett Packard in our design guidelines, and I've seen it in other places since, probably because of the HP documentation, although that may be my own bias on the subject, is that if the electronic box itself is about 5 degrees Celsius warmer than the environment, continuously 5 degrees just above the environment, it is very difficult for humidity to condense or to form inside of that. It basically creates a dry environment by just that temperature differential of just staying above it. The hard part is, like Dan, you're talking about those cockpits when they have hot, humid air and then they blast away at air conditioning and they have these rapid changes. Or I wear glasses. If I walk out of an air conditioned building or into one, or and I get this rapid change, the warm, moist air will just immediately condense and fog up my glasses. Even more prevalent now with the mask on for COVID. But the idea is that, yeah, you can. It's, as Dan said, very difficult, but over time, even hermetically sealed ones will still end up with some diffusion of moisture into it. So it's moisture and oxygen really like going to equilibrium. It's like a vacuum, right? If you've got a vacuum, it abhors, nature abhors a vacuum, so it'll try to fill that space. If there's not enough oxygen inside a element, oxygen will permeate it, and same with moisture. So it can be done for some duration of time, but it's, as Dan said, it's very expensive, right? So another comment or question from Lan Chun: how to prevent moisture trapping under conformal coating? Oh, that's a good one.
Well, you got to keep
Don't
it from
do
cracking.
it outside in Florida.
Yeah.
Yeah, don't do it outside in Florida.
Yeah, it's tough. So
but part of it is,
go ahead.
well, I was going to say is, you mentioned part of it is you've got moisture in the airlines, right, for painting, in factories that are, well, I know in factories I worked with in Asia, where it's a very hot, humid environment in Malaysia and Singapore and handful of these other plants I visited. um, they spent a lot of money to make sure that the facility was air conditioned and desiccated. So inside was a very dry environment. And that was one way they went at it. And the second part is in the conformal coating process itself is the we didn't advocate baking the products before putting the coating on, but it would basically be have warm products compared to the local air, which tended to drive away moisture. It wasn't perfect, but it helped prevent a lot of problems with that. So it's one way to do it, um, but you do have to think through the airflow, the sources of moisture, uh, the humidity and fluctuations, temperature fluctuations, and even the delivery of that coating. It has to be dry, and so there's a lot of steps that go into doing it well. Um, yeah, conformal coating is a great technology. You talked about it, Dan, as a barrier, but it it's difficult to get it right. It's been my own experience.
Yep. Hey, Fred, can you talk a little bit about what causes computers to get hot? For example, I've been to the biggest data center in the United States, and they get these rushes of data, and
Mhm. It warms
the
up.
data
Yeah,
goes
it's
through these
just
machines,
it's
and
just
it gets
current.
hot.
Yeah, it's just current. You push an electron along the line. There's a force there, and the copper or the steel or whatever conductors you have, even inside silicon, is there's resistance. Every electrical line has a resistance, and resistance manifests by creating heat. It's like rub a piece of sandpaper or your hands together, right? You rub them back and forth. There's a little bit of resistance, and it generates heat as a byproduct. And so, in these very dense populated silicon chips that we're using in servers these days, um, one of the biggest issues is how do you get the heat out of it? How do you keep it cool? And made lots and lots of progress over the years, but the more we push through those things, as you were talking about earlier, Dan, the more resistance it sees, the more heat it develops. So yeah, that's one way to get it. So Evan says, good explanation, thanks. Vivid explanation, which is a vivid response. Thanks, Evan.
Okay.
Stephen asked the question, what is the expected life or reliability for desiccant materials that can't be replaced, serviced inside devices that may be continuously exposed to steam sterilization, such as an autoclave? Well, 30 seconds, I would imagine, if you're inside an autoclave.
Yeah, and
Yeah.
so obviously it
I
depends
don't think
on
the
time
purpose
and
is,
temperature.
if you're, yeah, time and temperature, but if you're using an autoclave to sterilize something, um, desiccant material for in your packaging or all those kind of things, anything that's going to trap moisture is probably not going to survive the sterilization process. You probably
Yeah,
really don't want to put it in there. Yeah,
yeah.
that's kind of just asking it to fail. Yeah, anything, does that make sense, Dan?
Yeah. I mean, if it's just bombarded all day long, you may need a vent or something. I don't know. Uh,
You have some other method to
yeah,
deal with
some
that.
other
Yeah.
method.
Okay, and Rue is asking also, are you aware of any standards and design guidelines specifically about moisture control of optical components in an enclosure?
I'm not.
I'm not. Yeah, I mean, it's very much, in my opinion, and from my experience, it's very similar to what you've already been talking about, Dan. It's I mean, putting a barrier on it or film or grease or whale
Yeah,
blubber on an optical encoder is probably not a good idea. You're going to distort the lens that you're actually trying to deal with. And you have to be careful if you've got an IR sensor and um, you don't want to put something on it that's going to inhibit its ability to see what it's supposed to see. And then there's a range of different optical type devices that rely on some wavelength of light to work. So coatings and coverings and films and things like that, you have to be careful that they don't destroy the very functionality that you're looking for. The other part of that is, it's kind of what Dan talks about is using these desiccant. Can you control the humidity within that environment so you don't get condensation? And so a combination of managing the heat and thermal cycling, the amount of available moisture so you don't get to condensation points that you get puddling and fogging type things from occurring. If you can get it just below the dew point essentially and keep it there, you're not going to get this condensation. So it's one way to go about doing it, but it takes thinking through your entire design and how it's used. So it's not a simple answer. And then in some cases you can do ceilings and enclosures combination with silica or with the desiccant type systems, or by desiccating the air and pushing that through. I mean, there's lots of solutions for it, but it really is application dependent and what features you have. Right. I got another question. Ruth, thanks again. Another good question. Is a metal enclosure with lid with gasket seal considered hermetically sealed? No. It's closer to one, but it's not.
What's the definition of hermetically sealed? You're trying to remove. What's your definition of hermetically sealed?
Yeah, one of the definitions that the common one that comes immediately in my mind is that it deals with that you're not it's moisture will not go across that barrier. And,
Gotcha.
and I don't know if it usually involves with a long period of time. But just enclosing it in a can doesn't mean it's hermetically sealed. It makes it a given object airtight is kind of the quick definition of it. Metal is less permeable to moisture. It's not that it's not permeable. It can. It just takes a long time. Glass is also permeable, but it's a very slow process. So we tend to use glass and metals to create seals. The hard part with seals, hermetically sealing, is the welds or seals or gaskets and those kinds of things of maintaining those in a functional way. If you put a lid with a rubber gasket on it, the rubber itself is going to be permeable, much more so than the metal. And so now it's a path. And so hermetically sealed is almost always welded or sealed, formed in such a way that there's metal on metal all the way around. So you don't leave a path for moisture to go through it. And where it's really critical is then they will overpressure systems. They'll do all kinds of exotic things in order to, like you were talking about earlier, Dan, is like nitrogen flooding or bath or overpressuring, so to just disallow moisture from encroaching. So they can be pretty exotic and pretty expensive. But yeah, I am thinking of the small electronic enclosures that we have on circuit boards, like for a crystal. They are not hermetically sealed. They're a metal can, and it's for protecting the glass, this crystalline structure that's inside of it, but they're not necessarily hermetically sealed unless specifically designed to be so. Let's see, and Peters, looks like you got the thanks for your presentation, and it looks like it's right at you said it right at 10 o'clock, so hopefully you enjoy the rest of your day. Dan, any last words here as we wrap up?
No, just pay attention to the moisture, pay attention to water, and once you understand that, you have a better chance of solving your problems.